是不是可以借此把应该是其实自己去的约到生活，这就是其实当演员的时候，
Are you still sitting with live stream? No, it's on. I got a question about the homework. So, I got slightly different error values. It's e to the minus 7 rather than e to the minus 8. Yeah, is that fine? Yeah. Because I found like a slightly more optimized way to calculate the batch normalization.
Yeah, that's not like the error.
Well, it's off like 10 times. So it's like 1, 0.
Yeah, but it's like the difference between 0 and like more 0.
Okay.
Thanks for putting up with the schedule for last week. I appreciate you working with my schedule. Any questions before we get started? Everybody start with the next homework? Yeah, go ahead, Anthony.
Yeah, you notice like the homework, the URLs in PyTorch are kind of out of date, and so is the API, because Linear kind of switched the dimensions, and that was kind of a headache.
That's true. That's actually happened fairly recently.
Yeah.
We should probably get those updated.
And all the links to the API are broken because they chopped off the page. Because when you go to the .nn, then you go to the
When you say to the API, you're talking about the docs?
Yeah, the docs. Yeah, and the API. The API changed too.
Yeah, you're talking about like the channel, like the dimension order.
Yeah.
Yeah, that's true. That changed fairly recently. I mean, it doesn't affect the way that it's, like you can still do the assignment, right?
Well, you have to do a little bit of critical.
Yeah. Actually, it's not bad for helping critical. But that's a really good point. I appreciate you bringing that up. I didn't think about that, but it's like basically I just like reran the homework and still ran, so I was like, oh, good.
And what happens when Google starts kicking us off the GPUs because they're mad at us for using it too much?
Well,
should we say like the $10 is like part of the class fees or something?
You can thank your university for not providing you with a single GPU to use, and you can go knock on their door and say, "Where's my GPU?" And you can be really grateful for Google for allowing you to at least get that far. I don't know what to do. you have to have GPUs to do deep learning, and the university doesn't provide any. So,
Well, can we just wait longer on CPU time?
yeah, of course. Yeah, I mean, you play all those kind of tricks, no problem. But I'm just saying, like, if it wasn't for collaboratory, we wouldn't be doing any of this kind of stuff. Which, you know, I don't know, just the way it is.
And when we train our last network, can we base our we can pretty much base our network off of something else, right? This is just the CI bar.
Well, I'm not sure what you're saying there, but maybe that's something that you should ask after class. We won't take a risk class for that, but the answer is probably yes. But come ask me and we'll do something like that. Anybody else started into the next homework? Yeah. And those of you who haven't started, are you feeling the pressure? Let's keep going. Hopefully you do, because it's shorter, but there's still quite a bit of stuff to work through. So please get started. Okay. So we're gonna continue with our kind of history lesson in convolutional networks using the ImageNet challenge. And so today is our part 2. We did part 1 last week. And as you know, well, hopefully you remember that we took a little detour looking at the old, like what maybe was the first kind of modern convolutional network. And this is back in 1998. But then we looked at the 2012 winner of the competition, AlexNet. We went into details here about how it worked, the different layers, things like that. We're going to continue in this way and move kind of through the years from winter to winter, and learn about like what changes were made, and what try to get some understanding of why the new architectures did better than the old ones. So we're going to move now to just 2013, and 2013 is this entry by Tyler and Fergus. It's known as ZFNet. No one ever really talks about this, to be honest, because it was basically AlexNet, but it just changed some of the architectural choices. So, like the first convolution was changed from 11 by 11 stride 4 to 7 by 7 stride 2. The filter sizes, the number of filters used in the COM 3, 4, and 5 layers we just used more of them. Like basically we had in the next year GPUs with more memory, so we took advantage of that, and no surprise, more parameters. This seemed to do, they could figure out how to make it work better. But more or less it was like the same architecture. So yes, it won actually quite a bit of reduction in that top 5 error rate from 16.4 to 11.7. So amazing how like a few choices made such a big difference in the performance, but like in the end, nothing really like interesting to learn maybe from the changes in the architecture. And really, you don't really, like you'll never go into like the model zoo in your favorite deep learning library and find ZFNet there. Okay. All right. So 2014, we actually have 2 entries on here. Obviously, only one of them won, but they were 2 very different architectures. Yeah.
Yeah, you mentioned like this, like model zoo a couple of times.
Yeah.
Is it kind of pretty common inside of like machine learning engineering to kind of pick from predefined models as opposed to designing your own architecture?
Yeah.
Okay.
Yep. Totally. Yeah, that's a great question. Yeah. Very, very often you'll pick one of the one of the models. So like we'll talk about ResNet here coming up, and these days. So it used to be for a while that like BGG, like AlexNet and then BGG were like these baselines that people would train. But then for these days it's like ResNet, and ResNet with Atom is like this kind of default choice that people make when they first start on a problem, and then if you need more performance, then maybe you start to make adjustments there. And these would often be just like in terms of depth rather than like severe architectural differences. And the reason for that is, one, like the network starts to become a little bit more like general purpose along the way. like a ResNet, in a lot of ways is very, like when we look at the architecture, you see it's like very kind of generic, as is BGG, but there's so many choices to make there that typically what is done is to, pick a good enough network, but then really sort of like work on the data side, like make sure that your data is really good. Like for instance, as far as I understand, there was a talk given by Andre Karpathy, who's head of AI at Tesla, and he basically said that like the main computer vision backbone in the self-driving with the autopilot technology in a Tesla, that backbone basically is a ResNet type of backbone. So he didn't give details, but it's basically a ResNet of some kind. So and his point there was like where we do a lot of the work is in preparing really excellent data sets to learn on, which is interesting to know since it's a pretty impressive product. All right, so we're going to talk about two different entries here. Obviously, there's only one winner, but they're very different from each other in how they kind of thought about going from like what AlexNet was to like different kinds of architecture. They're really different from each other, and you'll tend, like again, in these model zoos, you'll tend to find these there, and you're able to use them. Although again, like ResNet's sort of like baseline now, I would say. So let's go into this. So BGGNet. So what's BGG? So basically, it was like a kind of, I don't know, just a sort of simplification, thinking about like what it is we're doing in these convolutional networks as we're trying to go deeper and deeper, and just sort of simplifying the choices being made, and trying to like reduce to have as few parameters as possible while still maintaining a lot of capacity in the network to learn. So AlexNet had 8 layers as we looked at. BGDs, there tend to be other, like a couple different kinds that you would run into. 16 layer to 19 layer. It's just a difference in the depth of the network. But importantly, like what characterizes a BGG is that it's really only made up of 3x3 convolutional layers. Like the number of filters changes as you kind of work through the network. Stride 1, pad 1, right? So it's a 3x3. So if you just do a 0 padding, you're gonna maintain the spatial extent of the feature map as you go from layer to layer. And then with some 2x2 stride 2 max pools along the way to do this downsampling. And that's really it. If you look at this picture over here, you can just see, here's like a kind of a simple representation of AlexNet, and in these different BGGs, you can see, a couple of layers of 3x3 columns here with 64 filters, then a pooling layer, then 128 and a pooling layer, then 256 and a pooling layer, and then 512s and a pooling layer and 512s, and this is the same, but just you're adding a few more 512s between the pools. Like why exactly? I know one of you wants to ask that question desperately. Like, why is it like 3 instead of, or 4 instead of 3 or whatever? It's just it was tried and it sort of worked. And notice that the ends of the network here remain the same, right? The training ImageNet. So we eventually want to have a fully connected layer of like 1,000, so that those are our scores that go into our softmax and our loss. But these fully connected layers of 4096 or 4096 into 1,000. So like kind of keeping the spirit of AlexNet in some sense, without the weirdness of like splitting it across GPUs. But instead of there being like 11 by 11, 5 by 5, and 3 by 3 later on, it's just always 3 by 3s. And in fact, there's always multiple layers of 3 by 3 before you tool. And let's just think about this for a second. So, like, why are we using smaller filters? Why use smaller filters at all?
It's faster.
Well, we're trying to get, yeah, so faster. How is it faster?
You can shrink the number of weights because
Because like the number of weights is, the number of weights per filter is smaller, right? Yeah, that's true.
then you have more channels for the same.
Yeah, right. Like you're trying to have deeper networks, and you're trying to have like basically like more filters per kind of like block here of layers. So so you kind of like you need to start reducing the parameters somewhere to be able, to kind of, to make this not so expensive when it comes to, evaluating these, so doing the forward pass and backward pass. So one way to do this is just use 3x3, and like 3x3 is in some sense like the smallest convolutional filter you could use, right? Like we don't use 2x2 because, we always use odd numbers, and you can do 1x1, but you're not really getting any spatial. You're not learning really any spatial statistics with a 1x1. You're just learning to kind of like, recombine the channel dimension in a 1x1 convolution. So like 3x3 is kind of like the smallest. So it was just like, it was just like this approach of like, okay, let's just simplify things and reduce parameters and try to make deeper networks. And so that's what they did. And with 3x3s you have fewer parameters, and that just helps in this case. But importantly, like you're not necessarily giving up a lot of like capacity to learn. So, and here's the thought experiment here. So, receptive field is like when you think about these convolutional layers. If you look at like an activation map or feature map, and you look at any one of the like entries in that map, you can kind of like go back through the layers and think about like which parts of the previous feature maps were included in creating that value. So like in just one layer, it's like the 3x3, entries from the previous feature map that contribute to making this one entry in the next feature map, right? But if you put two together, think about the convolutional operation. If you go back 2 layers, what's the effective size of the receptive field for a single unit? Can you kind of picture that in your mind? What is it?
It's that squared, isn't it?
It's what?
It's that squared.
That squared?
Yeah, so it's 3x3, and then you do it again, and then that'd be like a 9x9.
Oh, yeah. I think like the intuition is kind of right there, but it's not the right answer. You're not because you're not squaring. What you're doing is you're moving that. Like you were 3x3, and now you got the ability to do like kind of 3x3s everywhere around that. So it actually ends up being 5x5. So you go back 1 and 2x3s, and for every single one of these, you go back 3x3. And if you just kind of fill out that that space, it ends up being 5x5. And if you go again, it would be back one more layer, it'd be 7x7, and that would be the receptive field again, like entries from the previous feature maps that are contributing to the value in like the current feature map. Does that make sense what I'm saying? Yeah, question.
So why don't they just use it 5x5? But they have to.
Oh yeah, that's the question. So how many parameters are there in 2 3x3s as compared to like 1 5x5?
Larger. More parameters.
18 versus 25.
Right,
Times
18.
whatever channels.
There's 18. Yeah, because you have to think about the channels as well. But there's 18. The channels are going to be the same. So there's the 2 3x3s. That's 18 parameters, right? 2 times 9, 2 times 3 times 3. But here we have 1 times 5 times 5, 25. So we're getting the same receptive field with fewer parameters. Of course, it's still fewer parameters. It means that like there's not quite as much learning capacity there, right? Like if there's fewer parameters, you can think of this as some kind of factorization of this kind of 5x5 convolution, right? Into 2 3x3s. But the good news is that you still have the same receptive field, so you're still allowing the same set of entries from previous feature maps to influence the activation there, the unit in that particular feature map. So that's the whole point of it, exactly. Is that you're trying to reduce the number of parameters. while still maintaining something similar to this, to the receptive field. So if you look at this, you know, like here's a 5 by 5 here, forget the 11 by 11, but you could more or less get the same, you know, like try to learn the same map from previous feature map to current feature map by putting together 2 3x3s. You just have fewer parameters overall.
We're keeping in we don't include channels in this, right? Because it would
What's that?
so it'd be 3 by 3, but then you also have number of in channels and out channels too.
Yeah, but I guess this, you know, like if those just remain the same, which I know they don't in the examples here, so like that's also a difference. But if they remain the same, there's fewer parameters in 2 3x3s. Okay. Right. Fewer parameters.
Can we also have universal logic too, since we have 2 layers now instead of 1?
Like the universal approximation theorem?
Yeah.
No, because, well, like yes, if you allow the filters to grow, right? Like the whole point of the universal approximation theorem was, yes, that applies, but only if you allow like the hidden layer to be, you know, like basically exponentially large with the number of inputs. And so we're definitely not doing that with, the whole point of convolutions is to not have a fully connected layer, but to have, you know, like fewer parameters, but still kind of, you know, be able to kind of cover the input space. So no, we don't get universality, but you're right, we do get more, like this part right here. It's deeper, and then therefore there's like more nonlinearity. So perhaps we have the ability to approximate like at least different kinds of nonlinear functions than we could with a single.
Like an exclusive
layer.
OR?
What's that?
Like an exclusive OR?
Well, yeah, I mean it's more complicated. Yeah, like that example is a little bit more complicated, but yeah, like you get the idea that you're able to do. Yeah, you're allowing, you know, these are just kind of a little bit of hand wavy arguments saying like, hey, things are better because you have the same receptive field size, but fewer parameters and more nonlinearity. So probably we're like learning, like, you know, it's a different set of functions that you can learn, you know, maps from input to output, but maybe it's better. And the point they're trying to make here is like we were able to make deeper networks, and we were able to you know, do a lot better on the task. So empirically, these are better in the end. Yeah.
Yeah, so like, for convolution networks, in every case, when we say that you have to reduce the filter size as much as possible and keep it as deep as possible to get better results.
That's certainly the kind of how the history lesson goes here, is that we're trying to go to deeper and deeper networks because we think that more depth allows us to learn more nonlinearity, which allows us to approximate more functions and do a better job at whatever task, the classification or otherwise. And empirically, that sort of works itself out for a lot of the popular tasks that we know of. There's no proof there that that's the case, but yeah, like we're trying to go towards more depth, and we have a constraint, which is like the amount of compute we can use, like the size of your GPU or number of GPUs you have, and so at some point then you have to start trading something for depth, and so you start reducing parameters. And as you get to ResNet, you'll see like a very clever way of doing this.
Are there any cons for this method, or is it beneficial?
Like cons for just like the basic approach of trying to go deeper and reduce the parameters?
Yes.
Yeah, there are some. We're going to talk. So we're not going to just focus on depth here in this. Like we're going to talk about other aspects of these networks, like other architectural choices that also kind of help, and that will start to address some of these problems. But again, like I want to emphasize that there's no mathematical proof here that's like these are better than these other ones. It's just empirically we think depth matters. Depth allows us to learn more interesting hierarchical representations of the data that then become better inputs for whatever task you're trying to do, like classification, object detection, localization. things like that. So this inductive bias, this convolution and depth, is like seems to work, and there doesn't seem to be like a fundamental limit to it either, except like in possibly data, the amount of data you have. Nevertheless, there's still a massive number of parameters here. So if you go through this, it's sort of fascinating to look at. So inputs at the top should sort of opposite of the way it's shown there. But inputs at the top, you see this like the size and memory, like the memory requirements at each layer for the feature maps, and then how many parameters there are in each of those layers. So as you start to work your way down, what stands out to you in like the pattern of things you see here? Like, where are the parameters in the BGGNet?
Bottom. I mean, near the input.
Like near the input? Up there?
Yeah, it's 3.2 megabytes, but near the bottom it's only like.
Yeah, so like, it's not surprising that the memory requirement is sort of decreasing as we go here, because we're really reducing the spatial extent, right? It's like quadratically we're reducing it. But how about in terms of parameters?
Oh, okay.
Where are the bulk of the parameters of a BGGNet?
Yeah, number.
Yeah, what we would call these days you would call the convolutional layers through to where we transition to the fully connected layers. We call that the backbone, and then the fully connected layers we would call the neck, and then basically the loss is called the head, and you can have multiple heads, and so they can have their own layers as well. But you have this kind of backbone, neck, head, or multiple heads. So they're all in the neck, right here. These fully connected layers. Like, look at this. There's over 100 million parameters in just this one fully connected layer. Because what you're doing is you're going from, like, by the time you get to this like final pooling layer here, you've got a feature map that's 7 by 7 by 12, right? So the spatial extent is 7 by 7, the 512 channels. So do that multiplication, that's a big number. And then you're doing fully connected, so like, the other part of the matrix has a dimension 4096 because that's the size that you're wanting for that. So that's fast. Like that's really interesting. If you just fully connected layers. This is why we do convolutional networks. I want to kind of point that out. Like if every single one of these layers here was a fully connected layer, this network would have, billions, maybe tens of billions of parameters, right? And especially in 2014, that was not a possibility, really. I mean, maybe it was, but no one was really doing that. So we don't do like convolutional networks, like introduce an inductive bias into the networks that we use, so that our layers don't have hundreds of millions of parameters in them, but instead they have, hundreds of thousands, maybe. A couple million or something like that, but certainly not 2 magnitudes or 2 orders of magnitude larger. So we are all memory requirements. You need 96 megabytes for a forward pass, and then there were a total of 138 million parameters. So again, 138 million total. 102 or 3, 17 million, another 4. Like, put those all together, that's like 124 million out of the 138. So most of the capacity of this network is in the final, like, fully connected layers. So this is just trying to illustrate to you like the cost of a fully connected layer. And you'll see as we go to like more modern networks that you tend to see shorter and shorter necks because of this issue. Yeah.
Yeah. Could you elaborate how you compute the memory? I'm not quite sure how you get.
Yeah. So it's just the size of the input to that layer so like, or the size of the feature map like at that layer. So so like input, your images are 224 by 224 by 3, times like whatever is the size of your like of your data type, right? So like these are probably like 32-bit floats or something like that, right? So I'm actually not 100% sure on the calculation, but something like that. And so in the next layer, it's just a convolutional layer, 3x3 convolutions, 0 padding, so you maintain the spatial extent, but now you have 64 filters, and so you do that multiplication again, and then times the size of each entry, so like a float 32, something like that.
Is this the memory to contain the network architecture?
Mm-hmm. Well, this is just so it's a good question. So it's just the memory for so not for the parameters, but just for like the feature maps. As you go through, and you're right. The model itself now has its own memory requirements. That basically are like the number of parameters times like the size of, again, like the data type, right? And that also has to be stored. And these days, you may be aware, you may not, that a lot of training is done in what's called mixed precision. So like some operations are done in like a float 32 format, but a lot are done in like a float 16, point 16, because obviously you're reducing the memory requirements, so you can fit more model, you can fit more like larger batches, and you don't seem to lose any performance. But like things like batch run, which we'll talk about later today, like are done in floating point 32 because it's thought that that's needed. But in these days you weren't doing anything like that. You just everything was done like in floating point 32. Great question. Yeah, this is just pointing out that like there's most memory early on, most parameters later on.
So could we create more convolutions and have a smaller, fully connected net?
Yeah, totally. Yeah, and you'll see like you'll see how the networks kind of adapt or how they evolve from year to year. Yeah, there's some common names to these things, but hardly anybody uses the BGG network anymore.
So why 3 fully connected layers? Why not 2?
I'm not VG or G. I don't know. It's just what they were doing. I mean, basically just because AlexNet did it, and I'm sure that like they just were testing that, and did a lot of changes to the backbone, and just kept the net fixed. Because you can only run certain experiments. It'd be great to run them all, but yeah, I don't know. The history lesson's deep, but not that deep. Okay, so as you saw, like this did really well, but it only came in second in the classification challenge in 2014. It did come first in the localization challenge, like actually drawing boxes around like the objects in the image, which we haven't talked about yet, but we will I think it's next week. So training was done in kind of similar ways to the AlexNet 2012. Notice that there are no normalization layers. The submissions just use 16 or 19. Obviously, ensembles. The entries are always ensembles. Every competition is always an ensemble. And then the fully connected layer, this like final 4096 here. For a long time, the pre-trained either AlexNet or BGGNet, like on something like ImageNet, this layer right here was used as like the representation of the image that you were putting into the. So like you have this large image, right? 224 by 224 by 3. But what you really want is like some vector representation of it, so you can like do things like similarity search or something like that. And so it turns out that like this representation here, like if you just were to forward an image through this network on any of these and go to like the second 4096 fully connected layer, and you just use that vector as the representation for the image, like that ended up being like quite good for a whole bunch of tasks. And we'll actually kind of see some of those examples as we go. But for a long time, like that was used as just a way of like saying, okay, well, I don't want to really work with the images, I just want to work with some representation of the images, so I'll just forward them through one of these networks and use those features, which is pretty interesting.
So are they using ReLU for their activation after each?
Yeah, ReLUs are all, yeah.
And when you mean, what do you mean by ensemble? Did they run this over and over again on?
They just train it a bunch of different times with like different, random initializations. They learn slightly different things, and then you, like we talked about it, I think the last time, right? Where you take three of these, they all sort of like they all will make their predictions. The way that like the ensembles work for all of these is to forward the image through each one of your net, like your train networks, different versions of the same train network. Get to the softmax so that you have a probability distribution, and then average the output from the softmax, all those distributions, average together, you get another distribution, and then that then becomes like the input to your last section. But like from there, you just read off what the
so they create like
the largest
a dozen
one,
BGG16s.
Yeah, just many of them, just different. You just train them all the same way, just using different random initializations of the parameters of the network. So, yep, that's like a typical. That's how you come up with a typical ensemble. Again, the idea there is that each one's loading something slightly different because they kind of started in some different part of the law space and ended up in a different part of the law surface, and like together they seem to like be able to kind of cover more of the examples. So it's like you're averaging out the noise due to initialization. Good questions. All right, so everything's kind of the same here, but then they use the kind of like initialization called Xavier initialization, and we're going to talk a little bit about that. So weight initialization. So what is weight initialization? So we haven't really talked about this much yet, but you've already run into this in your homework. But you have to start your network somewhere in the law surface, right? Basically, for each one of these connections, there's a weight associated with it. You need to kind of make a choice for what that is. And especially early on, especially like for AlexNet, especially for these like BGG and Inception, which is the next, or GoogleNet, which we'll talk about next week. Before there were a few more kind of architectural innovations that sort of made this less important. Initialization was really important. Getting the right initialization made it so that you could learn quickly and get to a good like local minimum and loss surface. So let's start thinking about weight initialization. So what happens if like all of your weights are constant? Just like they're all the same constant.
And everything's just going to be learning the same thing.
Say it again?
But you end up all the little convolution filters going to be learning the same thing.
They all represent the same thing? Yeah, that's right.
You need to break the symmetry and get the balls to roll to see all the little minimas.
Yeah, right. That's right. So like if you have a convolutional network, all our filters are the same. They're all kind of sorted out the same way. Are there any problems with that?
The loss will be very high.
The loss could be very high. Why do you think the loss would be very high?
Because there is no learning that the model has done in that case, and it will predict some arbitrary value, classification for that image. So it will be so far away from the ground truth because all those model parameters have to be tuned.
Mm-hmm. That's a good point. So we sort of expect that when the network has learned something optimal, that it's going to be nowhere near being the weights being constant. Like it's going to have to be something completely different. Like this seems like a really weird, like non-random thing, and that's definitely true. That's definitely true. So, and it's not that you couldn't learn starting from a place like that, but it is kind of an awkward place to start. So, weight initialization. Like what are some of the ideas that you would do to like, to instead of being like constant, just doing something random. So obviously you could sample from random distributions. So, kind of a first, maybe somewhat naive idea is just to, sample from a Gaussian with zero mean so that there's, as much, the probability is the same to sample like a positive weight or a negative weight, right? And then you could just pick some sort of standard deviation. So like you'd expect you maybe start with small random numbers. Why small? Why would it be good to start with small random numbers?
More overfitting.
Yeah, actually that's exactly it. Like overfitting is often associated with like really large weights, and so like being random already is kind of ensuring this is not going to be overfit. But if you start them smaller, kind of like in the range of the size that you want them in the end, that's expressed by your regularization, then like that's pretty good. Like the network doesn't have to spend any time like getting those weights into that kind of range. So yeah, something like that. I mean, again, all this is empirical. There's not like a whole lot of justification other than just kind of thinking through how you like to start these things off.
Does it matter if we use a uniform distribution or a Gaussian? Because this is uniform, isn't it?
Right. I mean, does it matter? Probably not. I mean, actually, it does. It does matter for some of the choices, as you'll see as we like look at some of the actual like more explicit versions of initialization. But yeah, like in general, like at this point, you use a Gaussian. The idea would be like use something kind of symmetric about zero, and you get as much probability of being positive as negative. Remember, we already actually talked about this a bit when it came to like ReLUs, and what did we decide there?
It likes to be zero-centered.
Yeah, there we decided that we didn't really want things to be zero-centered because we want, ReLU has signal when the activations are positive. So we wanted there to be some kind of bias towards having positive activations, and so adding a slight bias, like basically changing the mean to be slightly positive, actually helps in this case. But this is just kind of helping us to think through the issues here. So yeah, if you were to do this and you were to kind of play around, and this is not a bad thing to play around with to build up your intuition, something like this would work okay for small. When we say small here, we mean shallow, not very many layers. But it starts to become really problematic for deeper networks. So forget all the code on this page. Just, here's a bunch of code to say what we're going to do is we're going to kind of like set up a kind of just simple example to think about what happens when we start with a certain type of initialization in a network of 10 layers, so 10 layers deep. Each layer's got 500 units on it, and we're using tangent nonlinearities here just to be very like symmetric. So like there's no bias in this way. This, of course, things change quite a lot if we were to use a ReLU, but just kind of trying to build up some intuition about what happens in these networks in these kind of simple networks as you forward as you forward whatever the input through, starting from like some type of randomized initialization. So what happens here? So in this case, so like let's say that we send through Gaussian type data through our unit or through our layers of 500 layers each. And if we start with small, random, zero-centered weights, then what tends to happen is what you're seeing here, is that there tends to be a kind of contraction of the of the outputs at each layer until basically everything is like centered at 0. So the weights are small, so it's like reducing everything, and it's random. So like there's as much like likelihood to kind of increase as there is to decrease via the weights. And so because of all the symmetry, everything just kind of pushes towards the mean, and basically what was like kind of a rich distribution of input becomes just like a single output. And this is not good, right? Like we want to do classification in some sense, and like it depends on the units being distributed between -1 and 1, for instance. Then having all the outputs be the same is quite bad. So in general, like approaching the problem like this is a little bit bad. So what are the reasons why something like this happens besides what I just said? Like thinking in terms of like the layers themselves. Any thoughts? Actually, a little bit hard to reason about for the first time. But any thoughts on like what are like the important numbers from going from layer to layer that would maybe help prevent? Like what would we do differently to prevent this kind of collapse to the mean? Yeah.
Adding dropout.
Okay, adding dropout. Yeah, I would expect that to not affect things because that's like another random process on this random assignment of like either positive or negative, right? Like you're gonna have as much chance of removing positive as negative connections when you do dropout. So like I wouldn't expect dropout to change this behavior. Just it would reduce the size of the network, but not really like the effect of the weights on the outputs. Like on average, not like in any individual run, but on average. Yeah.
Make all of the weights initialize something above 1, so that you don't have like a vanishing gradient in the situation, if that's what's happening.
Yeah. So notice that there are no gradients here.
Oh.
Like we're just forwarding this thing through a network that's 10 layers deep, and just seeing that for the simple network that we chose for small random weights that are 0 centered, we just tend to get 0 out. Like we get 0. All that output gets squished to the mean of 0.
Or can you just stretch it back out after each?
Okay, stretch it back out after each one. That's not a bad idea. That is a.
The mean's pretty centered, so we don't have to.
Yeah, that's an idea that didn't come into these networks at this time, but it's used later in a normalization layer called batch norm, and we'll talk about that. That's a great idea. Any other thoughts? This idea of kind of stretching out or like thinking about the like sizes as you go in and out of these networks is about right. Yeah.
So can we make the weights of the earlier layers like kind of smaller and then get bigger?
Oh, that's interesting. Yeah. That's a cool idea. These are good ideas. Great kinds of projects actually for the end of the semester that kind of explore these ideas. Right, all activation becomes 0. We spent a lot of time talking about that. So here's something. No one said this, but here's another idea. What if we were to change this so that we made the weights quite large? Right, so instead of there being like 0.01, like the weights are 1. The randoms span in, fan out. So the span in is just like a number of things and a number of things out. This is just respecting the dimensions of each side. But let's say we just made it really big. What would happen in this case? Remember, we have tanh activations. So if we make the weights really big, what we tend to do is push everything out to be large. And when they go through the activation, they're going to be squashed to either 1 if they're positive, large and positive, they're going to be squashed to -1 if they're large and negative. And that's what you're seeing here is that if value is too large again, if it's 1, so it's 2 orders of magnitude larger, then we tend to get like this kind of opposite behavior where everything just kind of pushes out to be either 1 or negative. That's also really bad. Like, there's not, like unless this is a binary classification problem and you have all your like positives over here and your negative examples over here, this is actually quite bad as well. Like it's bad in a different way, but it's still bad. So, but notice that like it's kind of like it's like the other extreme. Like we moved away from the mean here, from everything being like the mean, and moved it out to the extreme. Okay, so like that kind of indicates that maybe there's something in between that would give us sort of better behavior. So what is that in between? Yeah, this is a really bad situation. So what's that in between? Well, there's some math you can do here to kind of think about, again, like fairly simple cases. Think about like the statistics of the outputs for layers like we discussed here. And if you kind of, if you kind of stick to those assumptions, then you can see that if the value that we multiply by is not some fixed value like 0.01 or 1, but is determined by the layer in some sense. In this case, the number of connections, coming, basically the size of the input coming into each layer. Then if we multiply by 1 over the square root of that dimension, then actually we are in a regime where we tend to preserve this kind of nice distributed output. And this is something that became known as Xavier initialization. If I remember right, it's because Gouareau's first name is Xavier. Could be wrong on that, I'm pretty sure that's right. And anyway, it was the initialization used for BGGNet for the competition. Again, if you go read the paper, you can there's like some assumptions made and some kind of hand waving that's done, and then it's like, oh look, the right parameter out there that would preserve like the variance as we move from one layer to the other is roughly this 1 over the square root of thing. And where do you see things like 1 over the square root is like statistics or probabilities?
Standard deviation.
Normalization.
Yeah, it's like standard deviation of some kind.
Normalization.
Yeah, like normalization.
It's the Z-score.
Yeah, like when you're doing like z-scores, like typically like if this is something like a variance and you want to divide by it, then you need to like take a square root. Like central limit theorem, has these kind of square root convergences with number of data or inputs. I don't know. There's a lot of kind of reasons why like 1 over square roots would show up in like preserving kind of second order statistics of distribution.
So what do you mean by assumes linear activation? So if we don't use Rayleighs, then this doesn't apply?
Well, what's happening is that we're using tangents here, but everything is done such that we're like in the linear regime of the tangent, right? And that's like the hand waving is that like we're actually using Rayleighs that don't have this like linear regime about 0. So like, should this also work in the case of the Rayleigh? You can't prove it mathematically, but it turns out that doing this very same thing actually tends to also work, and that's the hand waving part.
Don't we times by 2 then in that case?
Yeah, actually, that's a different kind of. We're going to get to it. That's a different kind of normalization. But you're actually right.
Because it's only half the.
That's the wrong intuition, but you're totally right. So well done. Okay. So anyways, the point is like this is a kind of initialization that where everything about it is determined by the size of the layer, like the input, like the size of the input, the size of the output, and and at least tends to work well for these kind of BGG networks. Even when you pass from like linear activations to very nonlinear ones like radius. Okay, so the point is that this is a kind of notation for talking about like the number of filters at each stage here, and this is like this is the ensemble used. So like there was a not just like retraining of the same BGG, but like even different like numbers of filters and like numbers of convolutional layers between pooling and things like that. But you put those all together, and you ensemble the results, and you can get this top 5 test error rate of 7.3, which was a lot better than the previous year, which was in the 11 something, but didn't win that year. It took second place. And then post submission, they were doing like lots of other ways of like making predictions on the test set. And if you get it down to 6.8, which I think would have won, but of course it was post submission. All right. Any questions on this? We need to get moving on to the other submission that actually won in 2014. But what I answer this. Hopefully, in some sense, like this kind of feels good because it's like really simplified, like the architectures in some way. Like it's just like we just do 3x3s and some pooling every once in a while. Like this seems to be good. In the end, it's not best, not by a long shot, but at least there's like some kind of rationality for like how you build up a network, a BGG network. Oh yeah, right. So now this is just we're going to move on to the GoogleNet, and I guess was this post? Let's see. No, this is just the ensemble. So this is just the ensemble here. So 6.71. So even still, BGG is going to beat GoogleNet. Now, GoogleNet, or what's also known as Inception Net, this ends up winning in 2014 the classification challenge, and it's called Inception Net because it's super weird. So where BGG is like very straightforward in terms of like how you build it up, GoogleNet or Inception Net is like anything but. And here's what it looks like. So it's built up out of these what became known as Inception modules, which have multiple paths from the input to the output, with various different kinds of convolutional layers. And you can see like this is the architecture here, where you have convolution layers and some pooling, and then you do a bunch of these modules, and you'll see some like these weird like parts of the network just kind of are hanging off there. What the heck are those? Where BGGNet was super straightforward, this thing is like totally weird and different. And yet it won, so it warrants our taking a look at it. So a couple of different things. So one is that it's a lot deeper than like, well, I don't know, a lot. BGG 19, like 19-ish layers, 22 layers. But it uses this Inception module. We'll talk about it now. Notice that well, you can't really tell from this picture, but there aren't any fully connected layers. So this thing sort of skipped fully connected layers entirely. And impressively, this thing only has 5 million parameters. So remember that BGGNet had about 138 million parameters. This thing's only got 5 million parameters. So, yeah, like that is a lot less. And then the winning. So this thing's like way more efficient to train. So, and it has no fully connected layers, so it's not surprising that this thing has far fewer parameters, since we saw that most of the parameters existed in the fully connected layers. So what's going on with GoogleNet or Inception, as it really become called? So, yeah, this Inception module is really, yeah, it's like taking various kinds of different convolutions and putting them all together into one layer. So let's talk through this. So what does it look like? So hopefully you can see this. You can kind of blow it up like this. This is the naive Inception module. If you remember, the actual Inception module has kind of like this additional processing layer here, but we're gonna talk first about the naive one and then add those in. So what's going on here? So the idea of an Inception module is that you have your feature map from the previous layer, and instead of making a choice about having, like, say, one convolutional, like one filter size, you say, well, gee, why not have a whole bunch of different filter sizes? And why not just do some pooling while we're at it as well? And so basically, there's, what an Inception module is actually many convolutional layers kind of run in parallel, and then concatenating the output from each one of those to be like the feature map that is the input for the next layer. So you have 1x1 convolutions, 3x3 convolutions, 5x5, and then this 3x3 max pooling layer. All the filter outputs are, concatenated depth-wise, right? So it's just lots of channels. So however many filters there are here, so you would use no padding here with 1x1 convolution, 0 padding here, like a pad of 1, 0 padding with pad 1, and 0 padding with pad 2 here. So that the spatial extent was the same for the output of each one of these, so that you can just easily concatenate them. And then that becomes the input to the next layer. So, a bit weird, right? Like, we haven't seen anything like this yet. We really thought about these things as being like kind of serial, one layer after the other. Yeah. So maybe this seems like a good idea because we have lots of different kinds of like convolutions, like we can learn different kind of spatial patterns in 5x5, different from 3x3, different from 1x1. But in general, like, what's the problem here? Like, you saw that there was only 5 million parameters, but you should be really skeptical of that right now, because why?
7x7 or 5x5 layers are a lot more sufficient.
Yeah, exactly. I mean, like, we just said that we want to use multiple layers of 3x3s to like, approximate what a 5x5 is doing with less parameters. And not only that, this is not just doing like a 3x3, it's doing a 5x5 and a 3x3 and a 1x1. So there's a whole bunch of additional parameters here. So, like, on its face, this should be more, and there's 22 layers of this stuff. So, like, this shouldn't be more efficient. But it is, and that's because this is the naive Inception module, and not the Inception module. So, let's just think through this real quick. So, let's say that our input at this point is 28 by 28 by 256, and that we have 128 1x1s, 192 3x3s, 96 5x5s, and then the 3x3 pooling. Okay, so what's the output size of the 1x1 with, I'm just looking at time here because you might be getting a little bit behind it, but what's the output size of the 1x1 with 128 filters? This is the easy one.
28, 128.
Yeah, 28 by 28 by 128. What about the next one?
28 by 28 by...
Yeah, actually, they're all easy, right?
Yeah.
Like they're all preserving 28 by 28, and then just the number of filters. This is how many you choose here. So you get, for 3x3s you get 28 by 28 by 192. For the 5x5s by 96, and then 3x3 pooling. It preserves the size entirely. You just doing this pooling, and there's no, like, the stride here is 1 with some zero, with like something the appropriate kind of padding. So you preserve the 28 by 20, the 28 by 20 spatial sense. So this is kind of a weird tool. It's not used to do like spatial reduction. It's just like another operation that can be done. No parameters, just pooling. So the final output size is just, it's 28 by 28, but you're going to add you have 128 filters here, and 192 here, and 96 here. There's, technically 256 there, the size of the feature map anyway. So we got a 28 by 28 by, add those all up, 672. So there's actually like a massive number of like operations happening here. So this can't be more efficient. This can't be. So how do we make this more efficient? And this is the beauty of the one-by-one convolution. And this now becomes like a really important feature in building out future architectures like ResNet. Is an efficient use of one-by-one convolutions to reduce depth. So what the problem really is here is that we've got 256 filters, like we have 256 channels here. So anytime we do like one of these convolution operations, we have to, whether it's 1x1 or 3x3 or 5x5, we still have to do that operation times 256, right? So what we really want to do is change that number 256 to be something much smaller before we then do these like spatial operations. And that's what we do. One by ones. That there's maybe many ways you do it. This is a learnable way of doing this. It's just to do a one by one. So it's essentially like at each entry here, just a dot product, through the channels at that entry, with some learnable weights that are shared as you move from entry to entry. So, and the key here, of course, is like if you want to reduce this, from 64 to something smaller, say like 32, half of them, then you want to have 32 of these one by one filters, and that's what you do. So, if you look, so this was the naive Inception module. The actual Inception module, before doing the 3x3 and the 5x5, actually has some one-by-one convolutional layers that are there to do nothing more than shrink the number of channels in the input, and then do these expensive 3x3 and 5x5 convolutions, and then concatenate all that stuff together, giving you a bunch of channels. Notice that the 3x3 max pooling actually adds some additional learning on top of it. It has an additional one-by-one convolutional layer. So that actually is adding in a bit more computation than before, but again, one-by-ones tend to be very efficient because you're just doing this like dot product channel lines. So these are often called bottleneck layers, and you kind of visualize that, right? Like you're taking like this really large input, you're kind of now trying to jam it through far fewer, like a smaller set of filters, and bottleneck. You're trying to push all this like large data through kind of a smaller neck of the bottle, and this actually tends to have a lot of really like good features to it. It tends to make the network use those features, like maximize the information content across those features. So instead of there being redundancy, in order to be able to maximally learn whatever the task is, it's going to have to try to make those like features independent of each other. At the same time, while you're trying to like regulate this thing and enforce that math in this case. So there's this kind of give and take there. But this is how the BGGNet Inception module sort of solves the like massive computation problem. So if you in this case, if you first do these 64 by 64, these one-by-one convolutions with 64 filters, then the total number of operations required is no longer times 256, but a fourth of that. And this kind of like factor of 4 reduction thing is like a pretty common choice. So we were at 854 million operations. Doing this in this case got us to 258 million. So it's less than half of the total operation. So quite a bit of savings, and still you have all of these different spatial scale filters. So that's your this is the crux of a BGGNet. Is this Inception module, and they're stacked they're stacked up, as you can see, like in that final picture of the architecture of the array. So if you look at this a little bit further, the full architecture, we now take that picture, we turn it on its head. So you have this kind of, before you see any Inception module, you have kind of your basic, convolution pool, well, convolution pool activation, Rayleigh activation, convolution Rayleigh activation pool, kind of architecture. Like this is looking a little bit more like an AlexNet or a BGG, but then you input this into these Inception modules, and you basically do Inception modules the whole way along. However, there are these at the very end of this, this is your, this is like your head, where you go, you take all this output, you have one layer to transform that into the correct length vector so that you can do softmax and classification. But then you have, so remove all the expensive, like the large four-vector layers. But then you have these things here. And these things here are basically, they're other heads. So they're other heads, but instead of them being at the very top of the network, they're at intermediate locations in the network. But they're classification heads in there. So they're basically taking whatever this output is here, turning it into a vector of length 1000, and then passing that through softmax, and then computing a loss from that. And it's the same here as here as here. So basically, the loss function is a combination of the three losses computed at each one of these heads. And the reason they did this is because this network was getting so deep that the gradients were starting, the gradient information were starting to quote unquote vanish, right? The gradients were starting to get small. And so they basically kind of powered this thing up by injecting additional signal from losses that were kind of closer to the input. So it's all being supervised by the same labels. It's just that you get signal up there, and then that kind of attenuates to these modules, so then you inject it again here, that kind of attenuates to these modules. So you inject it again here, and it kind of attenuates, but it's close enough where it allows for the whole network to be trained. So that's kind of weird. And you'll see as we go to ResNet in the next lecture, you'll see that we deal with these vanishing gradients in a totally different way. But this is how they were dealt with here, and it seemed to work great, at least for 2014, because they won.
They won, but it's that much more complicated.
They won, but it's funky, right? How many of you already are just preferring BGGNet to Alex or to GoogleNet? The simplicity of BGG is really nice, right?
That's
But then you're only thinking from I don't know, the perspective of a human looking at these things. Remember, this thing, despite it being so weird, has far fewer parameters. And even though it has far fewer parameters, it seems to have a greater capacity to learn, because of course it did better on this task, right? So in many ways, this network is better. But it just comes at this cost of this weirdness in terms of just thinking about what's going on in this network.
What is stack computing through the network? How do the gradients from one head combine with the other head?
Just addition. If you remember, they're just independent signals, and remember, we're talking about gradients, we're talking about rates of change, and so one is contributing to the total rate of change at that wherever you are in this network ends up being the sum of all of the rates of change from the different parts of the different. It's inputs as you go backwards, but it's from these different outputs, from the different signals. So yeah, they just add together. Super simple. thank goodness calculus in the end is really quite simple in terms of like the operations. So yeah, so it wins, and these things become known as Inception networks, and there are various different like improvements on Inception, like through the years, and just to mention a couple here. So like V2, V3, they start to improve on the training by doing a couple different things, including adding this thing called batch normalization. Batch normalization becomes this like really important way of training really deep networks. And we're going to take the rest of this time to talk about it. It's actually a very simple idea, but ends up being like really critical for training deep networks. So what is it? So this gets introduced in a paper in 2015, where the authors are also authors. We're also part of like the BGGNet paper or submission. And the idea is the following: you have your mini batch, and you forward it through through your network, and after each layer you have this feature on this output, and it could be kind of like really like the distribution of that data could be really different from batch to batch. And you might think like, okay, no big deal, but the problem is that the next layer in the network, from mini batch to mini batch, is being challenged with like very different statistics of the input. So like, if there's a way to sort of normalize that, or make those statistics kind of the same every time, then the next layer isn't as challenged to learn like this kind of non-stationary distribution from batch to batch, but what appears to be more like like a regular kind of input. And that's the idea behind batch normalization, and it's quite simple. You take your batch, and you transform it in this simple way. You compute the mean of the examples in that batch, channel-wise, and you subtract that off, so you have like a zero mean input, and then you divide it. So this is called normalization, but really it should be called standardization, if you know your statistics. But you then divide by basically the standard deviation of that same data, again channel-wise, and you now have this standardized output, meaning that the batch of data that's going into the next layer is not necessarily like a standard normal. It's not necessarily normalized normal data, but at least it has a zero mean and a unit variance or unit standard deviation. And this actually really simplifies and speeds up the training of deep networks, because again, you don't have this kind of non-stationary distribution every time you send you forward a new batch of data through the network. So it's really quite simple. So like slower here, it's you compute you're from that batch the empirical mean and the variances, and you standardize using those. It really should say standardized. So it's called batch normalization. And then what you do is you just basically, at least what was done kind of early on, there's some of this stuff has been looked at closer and conventions have changed. But you basically, after every activation, whether it's TAX or RAILU or whatever, you put a batch normalization layer in before the input to your next layer, whether it be fully connected or convolutional or whatever. And so now, the data that this layer is seeing every time, while it might not be normal, it's at least got a zero mean and standard and a unit variance. So, just like the statistics of that distribution are the same.
Why before the non-linearity? Why not after?
It is after. What's that? Oh, yeah, before. Yeah, sorry, I said after, didn't I? It actually is before, but your question is still the same. It's now after, by the way. But why before? I don't know. I don't know why they did it before. I think the idea was that, especially with like a symmetric, activation like tanh, that this was just preserving, like this, this was like order preserving, and so it was thought to not. I mean, in the end, all of these things end up being just like empirically it worked. It actually, if you look at like in your models used again and see where these are put, it's actually after the activation now. But at this point in this paper it was before.
Because if you put the Batch normalization after like a affine layer, it's like the mean shift, just like this bias. So
Yep, yeah, that's exactly right. Okay, so I think we're about out of time here. So, okay, so there's one more thing about batch norm that I want to say, and then I think we'll be done. So, just to kind of address your point about the like this affine, like possible affine changes. So this is the standardization operation, and this is the transformation. But the actual layer itself, the authors here thought, well, why not just throw in a couple of learnable parameters and see if actually it makes sense to learn for each layer, a transformation that would scale your data, basically change the variance, and then learn the bias term, which would then shift like the mean around from 0 to something else. And so each of these batch norm layers have these additional learnable parameters, a scale and a bias, that if the network wants to change the scale or change the bias, it can. It doesn't have to. Like you could learn this to be 1 and learn that to be 0, and that's actually how you like initialize the parameters when you're training these networks. But it could change it, and often they are changed. And this actually helps quite a bit. So again, like the statistics are going to be the same because, like, while this is standardized, the layer that the next layer is going to see something that is has mean beta and standard deviation of gamma, but at least it's always the same for every single layer. Okay, so yeah, this is the identity. Yeah. So that's batch normalization. I think that's the end of it. Oh, yeah. Let me start with this next time. I don't want to rush this because this is important to know here. So we'll stop there. There's like 2 or 3 slides left here, and then we'll finish up part 3 and talk